Hi, my name is Bernard Brault, and I want to talk to you about uh, one of the most important equation, I think, in math and physics. It's the Euler Identity equation, and it's right here. And what it shows is these five fundamental constants in one equation, and that's what makes it really, really elegant. So what you have here is, of course, you got zero, which was somewhat a math discovery. People didn't think that zero existed. One is obviously probably the basic identity integer, and then you have e. This is the natural log or exponent. So the derivative of e of to the x is equal to e to the x, and that's how you can derive that constant. The imaginary number, I never liked that term, imaginary number, but anyway, a square root of -1, it's not so imaginary. And pi, so pi being like a, no, and put together in one equation. And what I've been stating is that I think this equation here should be explained and taught before many other things because it makes so many things simpler. So in the first part, I'm going to show how you could use this identity to help find trigonometric identity. So for part one is how it simplifies trigonometry. But I'm giving you a bit of a warning because this is the boring part of uh, what this equation can do. So this talk here is going to be a little bit boring. So, but bear with me. Let's start with how trigonometry is taught using the unit circle in school. And then what I'm going to do is I'm going to use this equation right here and show you how much more powerful they could be. So let's get to basic trigonometry. What you have is you got a you have an x-axis right here, right? And you have a y-axis. So this is like a plane, and yeah, you draw a unit circle, and that unit circle is shown here in orange. And you can have a point anywhere on the unit circle. So it could be this point, this one right there highlighted, or this point, this point. And anywhere in the unit circle, that if you draw a line from the origin to the point, then you'll have an angle. And the angle theta is shown right here, right? So that's the angle theta. Um, and what you define the cosine of the angle as the coordinate of that point right here. It's the projection on the x-axis, so it's this length right here. That's the cosine, and then the sine is defined as, what is the y coordinate of that point, and so that would be the sine of the angle. Um, and I'd like to point out something about angles. Quite often people refer to angles as in degrees, and in math it's much more convenient to actually have them as radians. And I'm going to show you why. So you can you could say that there are 360 degrees, let's say, going all the way full around circle, and that's fine. So, and this angle right here, right? If the point was up there, this would be angle right here would be a square angle, and you say this angle is 90 degree, right? And going all halfway around the circle, 180 degree, and so on. But what's more natural is to calculate the length of this length right there. And this length right there is a measure, and that measure is called radians. So if you go full around the circle, then you know that the length of the circumference of a circle is 2 pi, right? So going all the way around is 2 pi. You go halfway around the circle, so you go all the way up here, and that angle right there, this is 180-degree angle, is in fact in radian. That would be pi because the length, that length here that I show is pi. So 90 degree is pi over 2, and 3/4 of the circle right there would be 3 pi over 2, 3/3 of pi, and going all the way around is 2 pi. So I just want to highlight that just to show you that using radians is a more natural way of actually expressing angles. All right, so let me erase this. And let's get to the first trigonometric identity, right? So everybody in high school has seen that when you have a right angle triangle, Pythagorean rule will say that a squared plus b squared equals c squared. So you have this same triangle right here. So a, this is would be a, so cos square right there, plus this is the b side, sine square is equal to c squared, but this is a unit circle, so that length is 1, so 1 squared is equal to 1 right there. And you have here your first trigonometric identity. Keep in mind that the projection of that point here is defined to be the cosine, and this here is defined to be the sine. And of course, it's cos square plus the sine square is equal to 1. That's just, basic Pythagorean theorem. Okay, so let's move to a few other simple ones. Whenever you measure angles in a unit circle, you start with the x-axis. So this point right there is angle 0, and you move up here, and this is the angle theta. Actually, this length right here is the angle theta that I show right there. So if I draw a minus theta, right, I go down there, right, this is minus theta. And what you notice is if you project minus theta on the x-axis, so that would be the cosine, that's the cosine of minus theta is the same as the cos of theta, because, that's this length right there is the same for both minus and plus and minus, versus the sine, right? So the point here in the y coordinate is plus this length, versus the other one is the same length except it's a negative sign. So sine of minus theta is equal to minus the sine of theta. So you can see here, you're just flipping this around. So that gives you identity number 2 and 3. And let's move with a couple of easy ones. Now what we're going to do is we're going to add 180 degree plus minus 180 degree to this angle right there. So you start with this angle, and adding plus minus pi, right, would be adding pi is halfway around, so it's just like a straight line, and you go all the way across on the other side. And minus pi would give you the same thing in this direction. So plus minus pi. And what you'll notice is this new point right there, its x and y coordinate are the same. So this length right here is the same as that length right there, except it's reverse in polarity. So this one is a plus sign, this one's a minus sign, but the length is the same. And the same thing with the cosine. So sine of an angle plus minus 180 degrees or plus minus pi is minus the sine, and cosine is same thing. You're just flipping things around. All right, so you have your identity 4 and 5. Let's do a couple of other ones. Instead of like adding 180 degrees, now you can take this point right there and you can actually add 90 degree. And 90 degree is pi over 2. That gives you this new point right there. And then you can do the same thing in the other direction. And this is like subtracting 90 degrees or minus pi over 2. And what you'll find out about this point right here is that the length right here, or its coordinate, are the same as the coordinate, but they're flipped, right? So in other words, this here becomes this length right there, and this one here along the y-axis becomes the x-axis. So you just got to be careful about the signs. So the sine of theta plus pi over 2 is the same as the cosine of theta, and then you get all 4 of them. And these 4 identities are, the x, y coordinate of this point gives you these 2 here, and the x, y coordinate, these 2 points gives you these 2, and you can work it out for yourself. And this is pretty trivial. So you got a bunch of identities right here. Now, if you want to do the other ones, that's where things get a lot more complicated, right? So let's get back to what I showed you earlier, right? So this time around, I don't have a x and a y axis. I have what's called a imaginary plane. So what I have is a complex number, and this is called a complex plane, and z here is that one single number, and it has a real component to that number. This is a real component, so similar to the x-axis, but this time it's the real component of the imaginary number z, and this is x, or the real part, and this is the imaginary part, right? So with the projection on the square root of minus 1 axis right there, right? So it looks the same as what we had before, except this time around what we have is a single number. And that single number is right here. And I'm saying that z equals to e exponent I theta. So that point z right there is equal to e exponent I theta. And as you increase theta, you can start at theta equals 0, it will be this point. And then if theta is pi over 2, you get up to this point. If theta is equal to pi, you get all the way down to this point. So more or less what we did before, except now what we call this point a phasor on a unit circle on the complex plane. And it turns out that similar to what we had before, the x, or the real part, is the cosine of the angle, just like we had before. An imaginary projection, or imaginary part of that number, is the sine of the angle theta, right here. All right. So, and we call this a phasor. Right? This point is called a phasor, and more so when the angle theta moves with time. So in other words, it increases as this point sort of rotates around the circle like this, right, at a constant velocity. And what would rotate around the circle at a constant velocity like this, for example, is a sine wave, right? Sine omega t or something like that, something that goes up and down in time. And you can have 3 points and space 3 points around the circle. I have this one, another one, 180 degree. And then you'd end up like with these 3 points rotating around the circle, and that's the equivalent of like what Telsa developed with the three-phase generator for current power and things like this. So what I want to show you now is, of course, if theta is equal to 0, right, in the case where theta is equal to 0, if theta equals 0, what you have is z equals e I times 0, which is e exponent 0, equals 1. And sure enough, at angle 0, right there, you got this point right here. Let me just draw that. You have this point right there, and sure enough, this is on the real axis is equal to 1. Versus if you have 180 degrees, right? So you move 180 degrees right there. So the angle here is pi. So what you have here, and this point right there, is equal to -1, and on the imaginary part, it's 0. So z when angle theta is equal to pi is equal to e exponent I pi, right? And that's equal to -1. And this is how I derived that. You move the 1 on the other side, and you have e I pi plus 1 equals 0. And that's the famous, identity that I gave you at the beginning, if you remember, right? So I said e exponent I pi plus 1 is equal to 0. And that's just a point, and it's the point on the complex plane of a unit circle that resides basically 180 degrees or at angle pi. All right, so how can we use this for trig identity? Okay, so for example, if you have e exponent I alpha 1 plus alpha 2, so what is that? That is, essentially again the unit circle, and you get alpha 1. This is one angle, and you had another angle alpha 2, so this would be theta 1. This is the second angle, and you had the two angles. And it turns out that this is equal to e exponent I1 times the other one. So when you actually multiply two phasors, you multiply their amplitude and you add up their angles. But in this case, the amplitude is 1 because we're adding all these imaginary numbers on the plane where that's a unit circle. So if it's a unit circle, that means that the amplitude is 1. And so what you do is you expand this. And what we're expanding this again, this expression right here, right, is equal, go back there, is equal to the cosine of the sum of the angle plus I times the sine of the two angle, right? So that's from, the equation. And then this one right here, if you expand this one into its real and imaginary component, this one is this, and I said you multiply by this one right here, and this one, when you expand it, it's this identity right here. So you have four terms. So you have the this times this, cos alpha 1, alpha 2, and this term times this term, you get a I square, which is a -1. That's how you get your minus sign, and the sign are multiplied. And then you have your two cross terms. So the two cross terms are going to be I sine alpha 1 cos, and you have that first cross term right there, and you get the second cross term. And you simply have what you have to say now is that the real part, and I'm showing the real part in sort of orange, and I'm showing the imaginary portion in green right there. So this here has to be equal to this right there. And that gives you this identity right here. And then the same thing with the imaginary part, right? The sine of the two angle there. So imaginary part's got to be equal to this right here. And that's the second identity, which is identity number 11. So getting through these, what is the cosine of the sum of two angles in terms of the sines and cosine of each individual angle, I think you can demonstrate that. I think it's been proven before without using this formula, but using this becomes fairly trivial and becomes pretty easy, right? So you don't have to remember this. All you have to do is just remember what I showed you. You can recreate this. So what if the two angles are the same? So if the two angles alpha 1, alpha 2 is theta, so then you would have the cosine of theta, or alpha 1 plus alpha 2. So you would have cosine of 2 theta. So what you have is this is the same. These two are the same, and therefore you have the cosine square and minus here the sine square. So you're getting identity number 12. And then you can use the first one we had, the Pythagorean one, and substitute the, for example, cosine here for 1 minus cos square is 1 minus sine square, and then you get that one, number 13. And again, same thing with 14. And you can do the same thing with the sine of 2 theta. In this case, you would be just the sine of this one is they're the same, and you just become 2 theta right there. So it would be the cos sine plus sine cos, and it would turn out to be 2 times sine cos right there. So I'm down to 15 identities right there, and the more complicated ones at the bottom right here, which they'll never show you how to demonstrate this because it's way past things they'll show you in high school. I'm showing you here how it can be derived, and you can do more than that. If you have, what about the sine and cosine of three angles? You add up three angles, and how does that translate? Well, all you have to do is repeat what I just said above, and this time around, you would have the multiplication of three phasors right there, and of course, you have the real part times the imaginary part of this first one times real part, imaginary part of that second one, a real part, imaginary part of the third one, and all you have to do is multiply these terms. This one here, right, its real component is a cosine of the three angles plus I, imaginary part, is a sine of these three, and you equate the real part right there and the real part of this multiplication, and that would be, for example, cos of theta 1 times this one. And then of course you need to have cross terms that cancel the i's, and if you have I, so if you take sine, sine, cosine, anyway, you work yourself through this, and I'm not going to do it here. You're going to get a very complex long formula, but you'll be able to sort it out and figure it out, and that's going to be your cosine equals to this part, and the sine of the three angles is going to be equal to that part. And that's about it. The end. All right, and by the way, this was the boring part about Euler's identity and how useful it is. Again, proving some sine cosine identities. Thanks for watching. Have a good day.